Okay, so yes, thank you. So first of all, I'd like to thank the organizers for giving me this precious chance to talk my recent work in this wonderful workshop. And I'm Satoshi Ikegaya from Nagano University, and title of my talk today is the anomalous proximate effect in topological superconductor hybrids. And in this talk, I want to focus on the nodal and conventional superconductors like D wave, P wave, and F wave, like this. And in these superconductors, the pair potential closes at a certain point on the Fermi surfaces, and the sign of the pair potential can change across the gap nodes. The striking feature of these nodal superconductors is that they can exhibit flat band zero energy states at the surface of the material. So this figure shows the energy spectrum as a function of the momentum part of the surface we consider. And in case of S wave, we have fully gapped spectrum reflecting isotropic gap function. But in case of D wave, we have a gap node at a certain point. But more importantly, we have flat band zero energy states connecting these nodes. And we can also find flat band zero energy states in P wave and F wave superconductors. And recently, it has been shown that these flat band zero energy states bounded in the vicinity of the interface is kind of topological object. Actually, the flat band zero energy states can be characterized by the winding number for each ky, so momentum depending winding number. So in case of S wave, the winding number is zero, irrespective of momentum part of the surface, so there is no flat band zero energy states. But in case of D wave, for instance, the winding number becomes zero in the region without any flat band zero energy states, but winding number becomes non-zero in the momentum region having flat band zero energy states. Therefore, the winding number defined by using the BdG Hamiltonian is well characterizes the flat band emergence of the flat band zero energy states. But at this point, we face a crucial problem, because when we introduce the impurities to the material surfaces, then the translation symmetry is broken and the momentum is no longer a good quantum number. It means that winding number cannot be defined in the presence of the impurities. So this fact implies that the flat band zero energy states seems to be very fragile against potential disorders. But however, we have known very drastic phenomena that clearly contradict with this simple expectation. And that phenomena is called anomalous proximate effect. So let me consider the nodal superconductor and normal metal junction. And here, flat band zero energy states appears at the junction interface. And we introduce the disordered potential to the normal segment that cause the finite resistance Rn. And we will focus on the zero bias differential conductance defined by the current and bias voltage applied to the junction. And this figure shows the zero bias differential conductance, numerically computed zero bias differential conductance as a function of the normal resistance Rn. And normal resistance is calculated by removing this superconducting segment. So in the ballistic limit corresponding to the left side of this figure, all the nodal superconductor shows the perfect transmission. However, by introducing the impurities to the normal segment, for instance, in case of D wave, the zero bias differential conductance decreases monotonically, and it finally goes to zero in the dirty limit. However, surprisingly, in case of PX wave, the zero bias differential conductance shows the perfect transmission irrespective of the strength of the impurities in the normal segment. So it shows perfect transmission. And in case of F wave, the zero bias differential conductance decreases at first, but it's saturated. And finally, we still get finite zero bias differential conductance even in the dirty limit. So by summarizing these facts, we can now realize that the zero bias differential conductance in the dirty limit is quantized like this. And in case of D wave, the index Z here is 0, but index Z for the PX wave is non-zero. NC represents the number of the propagating channels in the junction. And in F wave case, index Z is non-zero, but less than NC. So anyway, why this kind of very surprising quantization phenomenon occurs? So it has been shown that the flat band zero energy states originally located at the surface of the superconductor of the triplet superconductor can penetrate into the attached dirty normal metal. This statement is confirmed by the previous work showing the emergence of steep zero energy peak in the local density states of the attached dirty normal metal. However, this kind of quantization further implies that the penetrated Zerendis states retain Z4 degeneracy and form Z4 degenerate resonant states there. So if we can prove this fact, then we can explain the microscopic mechanism of the conductance quantization of the anomalous proximity effect. However, as I said before, the flat band Zerendis state seems to be fragile against impurities because the winding number no longer guarantees robustness in the presence of the impurities. So what the symmetry actually protect the Z4 degeneracy of the penetrated Zerendis states, and what physical origin determines the value of the index Z? These questions are last pieces to understand the mechanism of the anomalous proximity effect, and I will give the answer for this question in this talk. So the degeneracy in the quantum state is a kind of consequence from the symmetry of the Hamiltonian. And in this case, we focus on the chiral symmetry, which is defined by the anti-commutation relationship between Hamiltonian and unitary operator. And in the presence of the chiral symmetry, the eigenstates obtain two important properties. The first one corresponds to the Zerendis states. The Zerendis states must be the eigenstates of the chiral symmetry operator simultaneously. And at this time, eigenvalue, which is called chirality, becomes positive or negative unity. And the second property is related with the non-Zerendis states. The non-Zerendis states must be described by the linear combination of the positive and negative chirality states with the equal amplitudes. It means that, in other words, the non-Zerendis states is always constructed by a pair of the positive and negative chirality states. So by employing these two properties, we can now explain the physical origin of the index Z. So for this purpose, at first, we want to focus on the chirality of the flat band Zerendis states appearing at the clean surface. And for the clean surface, we can analyze the chirality of the Zerendis states analytically by hand. So we find that for the D wave, the number of the positive and negative chirality states is always the same at the clean surface. So by adding the impurities, all of them can find their chiral partner having opposite chirality and form non-Zerendis states. Therefore, the flat band Zerendis states of the D wave are fragile. But in case of PX wave, we find that all the Zerendis states have the same chirality. Therefore, even if we introduce the impurities, all of them can remain at Zerendis because there is no chiral partner having opposite chirality. And in case of F wave, we always find both positive and negative chirality states, but the number of them are different each other. So even if we add the impurities, some of them can find their chiral partner and form the non-Zerendis states, but we can always find the remnant at Zerendis with having same chiralities. So by summarizing this discussion, we can now describe the index Z by this relation. And here, n plus and n minus gives the number of the positive and negative chirality states at the clean surface. So now we can explain physical origin of the index Z. So then I want to explain the topological aspect of this index. So the winding number for the clean surface is related with the number of the Zerendis states with this relation. And the small n plus and small n minus gives the number of the positive and negative chirality states at the clean surface, no, at Ky. So the index Z is obtained by the difference in the total number of the positive and negative chirality states. Therefore, we can calculate the index Z by summing up the winding number for whole Ky. So now we realize that index Z is a kind of topological invariant, but it simultaneously characterizes the number of the stable Zerendis states at the dirty surface. So now this kind of integer number is called Atiyah-Singer index in mathematics. So now we realize Z is a kind of Atiyah-Singer index. So let me summarize my talk. So we now prove that the Z4 degenerate Zerendis states can be stable even in the presence of the potential disorders. Therefore, Zerendis states can retain the degeneracy even in the penetrated in the attached dirty number method, and they can form the Z4 degenerate resonance state transmission channels there. And finally, we can clarify a topological origin or microscopic mechanism of the conductance quantization of the anomalous proximity effect. And the explicit proof for this statement is given in this paper. So if you're interested in, please check them. So please, and let's move on to the second topic. So far, we have shown that the triplet nodal superconductor like PX wave and F wave can cause the anomalous proximity effect. However, this kind of superconductivity is quite rare in nature. So we have to break this stalemate, we have proposed the couple of hybrid devices that can show the anomalous proximity effect without employing any spin triplet superconductivity. So let me introduce these models. So for the first model is constructed by the three components. The first one is a persistent spin helix state, which is studied intensively in the context of the spintronics. And persistent spin helix state is described by this kind of Hamiltonian where we have quite tricky type of spin-orbit coupling potential, but it's actually realized into semiconductor quantum wells. And moreover, it has been theoretically shown that recently, two-dimensional field electric materials can naturally exhibit the persistent spin helix state. So now we employ the persistent spin helix state. And then we add the S-wave perpotential to this system. So now we get this kind of BdG Hamiltonian. And finally, we add the Zeeman potential like this. So we now get this kind of Hamiltonian. But more specifically, we consider this kind of hybrid devices. A semiconductor hosting the persistent spin helix state is fabricated on the insulator and superconductor junction. So only the segment above the superconductor, we assume proximity induced pair potential. So therefore, this semiconductor is effective NS junction. And by adding the right, thank you. So Zeeman potential, and when it exceeds critical value, we have two distinct nodal phases having flat band energy states. And we have confirmed that all of them have the same chirality. And since index Z becomes non-zero, we can get the zero-wise conductance quantization into dirty limit. So in other words, we can reproduce the anomalous proximity effect without employing the spin triplet superconductivity. And the second model, we use the D-wave superconductivity, but we don't need Zeeman potential. And in this case, D-wave superconductor originally hosts the flat band energy states at the clean surface, but the number of the positive and negative chirality states is the same. But due to the spin-orbit coupling potential, the number are shifted. And finally, it caused the final index Z, which is almost proportional to the strength of the spin-orbit coupling potential. And then we again find an index Z, the zero-wise differential conductance is quantized in the dirty limit. So then we again reproduce the anomalous proximity effect clearly from the spin singlet D-wave superconductor. So let me summarize my second topic. So I couldn't talk this, but to design these hybrid devices, at first we clarified the possible symmetry classes of the Hamiltonian for hosting non-zero index Z. And we have clarified that we need nodal superconductivity classified into the class BD1 or C2 symmetry classes. And on the basis of these symmetrical criterion, we have proposed two specific models showing the anomalous proximity effect without any spin triplet superconductivity. So these are a summary of my talk. So thank you for your attention. Thank you.
Okay, thank you very much, Satoshi, for the very nice talk. And now we have time for a couple of quick questions. There is a question from Victoria. Please go ahead.
Hello. Thank you for the very nice talk.
Thank you.
I have a question. Maybe I just didn't get it. Maybe it was very quickly.
Sorry.
So there was a helical state in quantum wells, like several slides before. You told it can be realized in quantum wells.
Ah, yes. This one.
This is thin blend semiconductor quantum wells. So what? You're saying it will be spin helix there because of what? Because of spin orbit?
Yes. Actually, in this case, we need fine-tune for the strength of the large spin-orbit coupling potential. So the 3-5 types semiconductor exhibit two different spin-orbit coupling potential. The first one is a Dresselhaus one.
Yeah.
And the second one is a Rashba one.
Mm-hmm.
And if the amplitude of them becomes equal, then we get this kind of tricky unidirectional spin-orbit coupling potential.
Ah, okay.
Yeah, so we are talking about this kind of stuff. Or if we make the thin film of semiconductor directed on 110 direction. In that case, we will get the Dresselhaus 110 type spin-orbit interaction and it is naturally described by this kind of Hamiltonian. So anyway, we have to make some fine tune for the strength of Lashba type. spill
Yeah. On the other hand, Rashba can be varied maybe with the gates.
Yeah.
Especially for these quantum wells are often used.
That's true. Yeah. So actually, this gives difficulty for realizing this system. Yeah, I don't like Rashba this time, but anyway, yeah.
Yeah.
Thank you for the question. Yeah, thank you.
Okay, then thank you very much, Satoshi, for the very nice talk.
Thank you.
It's time to move